So let's see one example here. So I'm trying to measure the solution meniscus is right here at the red line. So can you give a rating of this one? Okay, so you got first one, you got the 0.2. That's pretty good estimation, right? And 0 here, 1 is there. So what about I have a better instrument right now? Can you give an estimation on this one? With the better scale, you can approach to higher accuracy and precision as well. And your answer will have a more significant figures because there are more detailed scale on this one. When you making a single rating with whether a digital or non-digital measurement, look up an uncertainty in manual, or you can estimate plus minus 2 counts in the last digit. So just as what we did before, if value obtained from averaging small numbers of a measurement, you can use descriptive statistics to estimate standard deviation. By the way, we'll see that we can never get to the standard deviation because most likely our number of measurement is small, and then we'll show you how to get to the estimated standard deviation. Another example showing that, so if we are going to measure this result between, at this point between 5 and 6, if we use a better scale that can come up with 5.78, and the one we are going to do the measurement, when going to estimate the error, we use the last digit. So here, the last scale, it will be 0.1, right? The minimal scale in here is 0.1, and the estimate will be use 1/5 of the smallest scale, and 1/5 of the smallest scale will be 0.02. So in this measurement, you'll write to result at 5.71 and give an estimate of the error that's plus minus 0.02. So that's the how we report the uncertainty in a single measurement. Well, when you suspect there is a systematic error, and what do we do? First thing is usually use your lab notebook, and you probably write down something abnormal, and when you take that data point, then if you have something written, then you can make your judgment that that particular data point should be taken off because during the experiment something abnormal happened, and right now when I look at the data, probably that something abnormal caused the data point to be off. So if you have a lab notebook, you can use that to figure out if you can eliminate that particular data point or not. When you don't have enough observations in your lab notebook, you can do is the Q test to identify if there's a point can be thrown out of the average. The Q test can be used to exclude a single outlier, okay? But it's only one outlier out of a series of a measurement. If you think, okay, I have 2 data points I want to throw out. Q test is not designed for get rid of a 2 data point. So if you have a multiple data point that you want to throw out, you don't want to use a Q test. Okay, you have to rely on your notebook. In the Q test, we need to compute the Q value. That's basically the ratio of the difference between your outlying values and its nearest neighbor point and the total range of the value. So the Q equal to the questionable data point minus the nearest value data point, and take the absolute value of that divided by the data range. So range will be the highest data point minus the lowest data point. That includes the questionable data point. And then you can look up the Q table. If Q larger than the value in the table, you can discard the point. If Q is smaller than the value in the table, you need to keep the point. So there is a Q table available on Wikipedia. I put the link there. You can use the Q test table there. Here, I want to work on this example to see if one of the data point can be thrown out or not. So I was measuring the wavelength. I got these 5 data points, and there's a possibility this 0.21 is an outlier. So can we throw this out? Calculate Q. We use the outlier 0.21 minus the nearest data point. If we look at all these values, the nearest one will be 0.32. That's the second smallest. The range would be the highest data point. That's this one, 0.38, minus the lowest one, that's 0.21 among this 5. So after that, I got 0.65. Then when we look at the Q table, so I have 5 data points. So I'm going to look at n equal to 5. That's 0.64. The Q critical is 0.64, and the Q value we calculated is larger than that. So the data point can be discarded. When you look at the Q table, it'll show you confidence level. So this one is for 90% confidence limit. Then we can say the point can be discarded at 90% confidence level. So this is how we do when we find the outlier. If we suspect that there is maybe a systematic error, but we don't have a clue from our live notebook. If we have random errors, the treatment for random errors is usually use some statistics. So there is an assumption that if we are doing a good measurement, the probability of measuring a value that's close to the true value is greater than the measurement far away from the true value. So if the true value is here, that's probability or number of occurrence. When it's a good measurement, the measurement should be very close to the true value. So it should be concentrated in this region. And when the measured value is off, it should be less and less probable. So if we make more and more repetitive measurement of a value, then the measurement will cluster symmetrically about the true value, and eventually they'll give a kind of a Gaussian distribution around the true value. How many measurements will make us to get a perfect Gaussian distribution? There will be need at least 100 times of a measurement. So most of our experimental measurement won't be 100 times. So we'll use some other statistic to represent our measurement.